Since many Logisim users seem to want to create a graphics processing unit, or GPU, I figured I would try to address an issue I have always had with that idea, and that is that there is no way to have Logisim simulate a GPU in a way that would give the performance and capabilities of a modern GPU. In other words, it won't make your GPU and computer simulation faster, it would only make it slower. And it also wouldn't truly mimic a modern GPU. So I thought, how can the video system be made to perform better? I first thought maybe a dual-port RAM to give sort of a direct memory access or DMA capability to the video screen. But that would still be limited by the clock frequency. Then I thought, how about put the RAM in a new GPU component? That really clicked. The RAM could be loaded the same way Logisim RAM can be loaded, and the component could access its own RAM as much as needed, independent of the clock cycle. And for versatility, the RAM could also be set by your CPU. Being independent of the clock cycle would allow for not only memory-intensive things such as Blits and Sprites, but also less memory-intensive things such as lines, circles, polygons, and text. This is a video about this GPU component I made for Logisim. It's a jar library that can be loaded by Logisim and used in the same way as the video screen component originally from the Cornell version of Logisim. It's available at my GitHub page. A link is provided in this video's description. Later in this video, I'll show how to best access my GitHub repositories and show one that should be of interest. Since I didn't know if this idea would work, and if I could get Java to do what I wanted, I chose to go the easier route by first modifying the Java version of the CPU and computer simulator I wrote. That way, I would only be tackling Java issues rather than both Java and Logisim issues. For those who might not know, Logisim is written in the Java language. Once it worked and did everything I wanted, I tackled making a Logisim jar component from the new code I created. Sample circuit files are provided in the repo that have the GPU instructions for these test programs hard-coded into the RAM and ROMs. This way the GPU can be used by people who don't have a CPU design in Logisim. Since programming this GPU can be difficult at first, a very detailed help page is available by right-clicking on the GPU component and is also available on the GitHub page for this component. It covers such things as the GPU function codes and parameters, and the formats of the data stored in the GPU's RAM or ROM. Newer versions of the Holy Cross version of Logisim Evolution will open the help system using your web browser. The GitHub page also gives info on the sample circuit files included in the repo, how to build the component if you need to, and possible improvements. One major capability of modern GPUs is running shader programs written in a shader language such as GLSL, which is a version of C++. In order to mimic this capability as much as possible, I added the Run GPU program instruction. So far, each GPU instruction is essentially triggered by the clock cycle, which means that at most only one GPU primitive can be done on each clock tick. With the GPU program capability, one clock cycle can perform many GPU operations. All GPU operations are encased in a program block in the GPU's RAM or ROM. By the way, GPU programs can be nested, meaning a program block can call another program block, and so on. But I would say be careful with that. It can also be confusing calculating the address in memory to call, since every GPU operation in a program block requires two values, not one. One for the GPU select value, and one for the GPU data in value. To illustrate how one might convert a program written for my CPU and GPU, here's a sample code segment. This would assemble into this machine code. If you interpret what each instruction is doing, you'll see that this is what ultimately gets sent to the GPU, which is what we're interested in. Translating the GPU I/O addresses to GPU select numbers gives the final data. This data could either be put into Logisim RAMs or ROMs, like I did in my sample circuits, or it could be put into a GPU's RAM or ROM to use as a GPU program. If used for a GPU program, remember to put the end GPU program instruction at the end. And of course, either use would require the Logisim memory file header. Having shown that, I have to admit I didn't do mine that way. Instead, I modified my simulator to output to files everything that gets sent to the GPU when the assembly program runs. Could this be my version of Kobayashi Maru? I wanted to show some vector graphics in use, so I figured a rotating 4D hypercube, also known as a tesseract, would be nice. However, I needed the 2D data of the 3D shadow of the 4D object. I turned to a program I first wrote for the Sun Unix workstations. I later ported it to my Amiga and then to MS-DOS. Since I didn't feel like either booting up in MS-DOS or using an emulator, I chose to port it to Windows and add an option to output the 2D line data. It's somewhat no frills, but all I need is the data anyway. I then wrote a program that took the 2D line data and created the necessary Logisim memory files. Here's a version that doesn't use the run GPU program instruction. Clearly, that's unacceptable. Here's what it looks like using GPU programs. It might be hard to tell, but there does seem to be some flicker between frames. So I created a double buffer capability. GPU operations can be lumped together in a double buffer block, beginning with the start double buffer instruction and ending with an end double buffer instruction. Here's the other scene double buffered. Since all the GPU primitives in the first part of the program are lumped together in a double buffer block, it takes longer to start seeing something. But once it has processed all the primitives, they all appear at once when the end double buffer operation is reached. In order to add I/O lines for the GPU to my CPU design, I had to create a subcircuit for an I/O decoder because all 8 lines of the old decoder were used for the various devices, some of which aren't in this trimmed-down version of my computer. There wouldn't be enough room for a 16-line decoder, so it had to be put in a subcircuit. It also contains a priority encoder to combine all the GPU lines into a 2-bit select line. The GPU component also has an optional debug mode which prints all the GPU operations above the screen. It's off by default and can be turned on and off. Since when I wrote the test program, I never intended to have it continuously repeat, I didn't do a GPU reset or even a clear screen operation at the end of the program, so the sprites and Blits stay on the screen. I kept it this way since it looks kinda nice. At some point you have to ask yourself, will Mr. Smiley lick the equation? I think he can. Yes, he's really got that equation licked. The problem with having so many versions of my simulator is having to update all of them for any new features. So my Windows version of the simulator needed to be updated. One feature of the Java version that couldn't be done in Windows is the gradient paint. Windows has gradient paints, but they behave in a very different way than Java. The exclusive OR mode, or XOR mode, is also a little different. The HTML version also differs from the Java version. The XOR mode would be useless for rubber banding since it wouldn't fully erase the previously XOR drawn primitive due to anti-aliasing. And also, once again, the gradient paint capability is a lot different than Java's. And the text-based simulators needed to be modified as well, but obviously not as much. The easiest way to download a GitHub repo is to click on the green code button. Then you can download a zip file of the repo, or feel free to clone the repo, fork it, or star it. By the way, this is the HTML and JavaScript version of my simulator. It is well documented and includes my CPU's instruction set and assembler directives. A live demo is available in case you don't want to download it. If you're using the live version, you probably won't have the sample programs on your computer, so you should click the Examples button to select some programs I've included. Alternatively, you could use the provided assembler to assemble your own program. You can select the fast mode option, but be careful, because it can make the browser unresponsive until the program finishes. You can also disassemble the program. A light mode is provided as well, but personally I don't know why it would be preferred over dark mode. And don't forget my GitHub gist. It's an Amiga bitmap font reader I wrote for use on Windows and Linux. It could also be modified to run on Macs. Be sure to read the comments at the top of the code for important configuration requirements. My gists are available at this address. Clicking on afont.c will bring you to this gist, where you can click the download zip button. Here's some sample images I created with the loaded Amiga fonts. I put this code into a video text annotation filter I wrote. So not only can it load TrueType fonts, it can also load Amiga fonts. This gives a nice 80s style chyron. Well, that's pretty much it for now. I could explain in further detail how to program this GPU, but that would make this video much longer. Also, I feel the README file in the GitHub repo and the help page in the GPU component cover everything pretty well. Now to the inevitable question, can it run Doom? I still don't know if Logisim is fast enough, but this GPU component brings the answer a lot closer to not only yes, but also yes and playable. If you haven't done so yet, please subscribe, like, share, comment, etc. And if you click subscribe, click the bell to receive notifications of future videos. Even if you click the bell, still check back from time to time, since YouTube doesn't always notify subscribers.